Now, this video discusses about how we can have the equivalent capacitance and for the capacitors that are in parallel circuit as well as the series circuit. So before we go further, let's see types of actual circuits. We have two actually types of circuits. We have what we call the series circuit, and also we have what we call the parallel circuit. So we have the series circuit as well as the parallel circuit. And let's have the detailed structure about these two types of circuits. Let's start with the series circuit. What is the series circuit? Now, this is the circuit in which all components are connected in a single wire. There's no junctions in a series circuit. We can have, let's say, this is the typical series circuit. By the way, the capacitors are electronically presented with the electric symbol given as this. So two parallel lines represents the capacitor. So wherever I see this, just have to know that it is a capacitor. Now let's say we have, this is a circuit, that is a series circuit. We can have it as this. So this is a typical series circuit in which all capacitors are connected in a single wire. We can have this like that. And let's say this is the battery. We have that. In this case, this is, let's say, capacitor 1, and this is, let's say, capacitor 2, and let's say this is capacitor 3, and let's say this is capacitor 4. Now this is the series circuit in which all components are connected in a single wire. There's no junctions available, and all these actually components are connected in a single wire. Hence, this is the series circuit. So what are the properties of the series circuit? Now, in a series circuit, mind you, the capacitors are responsible to store charges. So in a series circuit, all capacitors stores the same charge. So there is an equal charge being stored in both capacitors. Should be in both capacitors. So there is equal charges. There is equal charges being stored in actually both capacitors. And also at the same time, the voltage is shared in these actually capacitors. So which means there is a voltage V1 across capacitor 1 on its own. There is a voltage V2 across capacitor 2. There is a voltage V3 across here, and there is a voltage V4 across here, since the voltage is shared. So the voltage is shared in the series circuit. So which means different capacitors actually consumes different voltages. And by the way, that voltage is from the battery. So the voltage is shared. So voltage is shared. That is for the actually a series circuit. And another thing is that in a series circuit, there is no junctions. So no junctions are available, as I've already said that all components are connected in a single wire. So keep that in mind. So let us see on how we can be able to find the total capacitance and for the capacitors that are connected in series, and I appreciate that. And let's consider this actually particular circuit. So mind you, since this is the actually series circuit, at each and every component there is equal charges being stored. So the charges being stored are the same at each and every component in that case. So at each and every component there is equal charges that are being stored. That is at each and every actually a capacitor there is equal charges being stored. So they keep that in mind. And what is being only shared, it's actually voltage. So what is the voltage across capacitor 1? So the voltage across capacitor 1 will be given as, the formula for capacitance is given as the charge divided by the voltage. So in this case, the voltage will be given as the charge divided by the capacitance. So we'll be using that formula. Now I have it as, there should be, the voltage across capacitor 1 will be given as, the charge divided by capacitor 1, and the voltage across capacitor 2 will have it as, the charge divided by capacitor, actually, the capacitance of capacitor 2, and also that of across 3 will have it as, the charge divided by capacitor 3, and also that of 4 will have it as, charge divided by capacitor 4. So now at the end of the day, this is the voltage being shared across each capacitor. And keep in mind that the voltage which is being shared, it is from the battery. So which means we'll have, the voltage from the battery is the same as V1 plus V2 plus V3 and plus V4. That is really making sense because the voltage that is being shared, it is the one from the battery. Now let's think of substituting those. Actually, let's think of substituting those. And now we'll have, the total voltage that is from the battery is equal to what is the V1? We have it as the charge divided by C1, and the plus the charge divided by C2, and the charge divided by C3, and that of the charge divided by C4. We'll have that. So since the charges are the same, then we can be able to factor them out. So in that case, we'll have the voltage being given as the charge times 1 over C1, C2, C3, and plus that of C4. So in this case, you can see that now in this case, you should have to understand that in this case, now you can see that in this case there is addition of the capacitors in this circuit. But what is the order of addition? Now the order of addition follows the reciprocal order. So since the addition itself follows the reciprocal order, then the combination of capacitors in a series circuit will also follow the same order. We'll have it as 1 over equivalent capacitance, and that is equal to 1 over C1 plus 1 over C2 plus 1 over C3 and plus 1 over C, let's say 4. So this is how we add the capacitance. Should be capacitors in a series circuit. So the addition of the capacitors in a series circuit follows the reciprocal order. In this case, we'll just have to make equivalent capacitance as a substitute formula. So in this case, I'm going to make equivalent capacitance as the substitute formula upon having everything here. So that's how we actually understand, that's how you have to understand about how we find the equivalent capacitance and for the capacitors that are connected in a series circuit. Let's say we have 3 capacitors connected in a series circuit. Let's say we have C1 that is given as 2 farad. Let's say C2 that is being given as, let's say, 10 farad. And let's say we have C3 that is given as 3 farad. And let's say these capacitors are connected in a series circuit. What is their total capacitance or equivalent capacitance in this case? Now, since they are connected in a series circuit, and the addition itself follows the reciprocal, in the sense that we have 1 over, equivalent capacitance, or we can say it as total capacitor. Total capacitance is equal to 1 over C1 plus 1 over C2 and a plus 1 over C3. We'll have that. 1 over total capacitance. Now the total capacitance, we'll have it as 1 over 2 plus 1 over 10 and a plus 1 over 3. Now we're going to combine these fractions. So let's start with the combination of these two fractions using the butterfly method. So in this case we'll have 1 over TC. By the way, whichever the way you can have to make TC as a subject formula will be acceptable. So in this case, using the butterfly method, we'll have 1 times 10, that will be given as 10, and a plus 2 times 1, that is given as 2, divided by 2 times 10, that will be given as 20. And in that case, we'll have that, and a plus 1 over 3. So we'll have 1 over, should be 1 over TC, that will be equal to, we'll have 12 divided by 20, and a plus 1 over 3. And using the same butterfly method, 1 over TC is equal to, we'll have 12 times 3, that is 36, and a plus 1 times 20, that is 20, and a divide by 60. In this case, we'll have so in this case, I'll have, let's say, 1 over TC, that will be equal to, we have it as, should be 56 divided by 60, and then we'll cross multiply. We'll have it as 60 is equal to 56 TC. Now in this case, TC will be given as 60 divided by 56. So this is how the equivalent capacitance or the total capacitance will be calculated, and for the capacitors that are connected in actually a series circuit. So as you can see, let me express that as a decimal number. Now in that case, we'll have it as 60, divided by 56. Should be 60 divided by 56. That will be given as 1.07. So in that case, we'll have TC being given as 1.07 farad. So that will be the equivalent capacitance in that case. So you can see that in all cases, the total capacitance, and for the capacitors that are connected in series, it is always less than the lowest capacitor in the circuit. So in this case, the lowest capacitor is given as 2, therefore the total capacitor will be less than 2. And even if we could have had, let's say, the lowest capacitor, let's say, being given as 1, it means the equivalent capacitance could be less than 1. So which means the more we are adding capacitors in a series, the more we are actually decreasing their actually equivalent capacitance. So keep that in mind. That is to say, if we had the capacitors, let's say 5 farad, let's say 6 farad, let's say 10 farad, I should have that, let's say 0.5 farad. Now since they are connected in the series circuit, you understand that the total capacitance, and for this capacitance, will be less than that, and it is always less than the lowest capacitance. So keep that in mind. So which means as we are adding the capacitance in actually a series, so the overall capacitance will be less than the lowest value or the lowest capacitance for the group of those capacitors. So take note of that. Now let's say we should have to understand about the equivalent capacitance in a parallel circuit. Now, what is a parallel circuit? Let's say we have, in this case, let's say this is we have let's say this is, now that is a battery, and we have, those. And let me have another capacitor here, and that should be given as this. Now in this case, let me have this one as a capacitor as well. And I should have this as the battery. Now this is, let's say this is the battery, and this is capacitor 1, capacitor 2, and let's say this is capacitor 3. Now this is the parallel circuit in which the capacitors are connected in. Now since there is a presence of junctions, now this is really typical parallel circuit. You just have to get it up. Now what are the properties of the parallel circuit? Now at each and every component, voltage is the same. So since this is the parallel circuit, voltage is the same at each and every component, at each and every actually capacitor. So which means voltage here is the same as here, is the same as here. That is the voltage from the battery. But now the charges are only being shared. So which means, the charges here are different from here and also different from here, but the actual voltage is the same at each and every component. So keep that in mind. But now this is happening because there is no any other capacitor which is being connected in a series with the battery. That's why we are saying at each and every component here, the voltage is the same as that from the battery. And had it been that we had another capacitor being connected in series with the battery, it means we could have had the voltage across that particular capacitor minus, we could have had, let's say, the voltage across that particular capacitor and the voltage from the battery minus that one, then the rest could be equal for this, because these are now in parallel. But let it be, we'll see some of the examples associated with that one, but keep that in mind, that since these capacitors are connected in a parallel with respect to the voltage itself, that is a battery, then the voltage across each capacitor is the same. Only that of the charges being stored are different. Now, in this case, you should have to understand that the charges are only being shared, but the voltage remains the same, as I have already said about that one. So, what is the total charge being stored by the capacitors? You see that it will vary. We'll have Q1, we'll have Q2, we'll have Q3, since each capacitor will store different active charges. But what is Q1? You should have to understand that Q1 is the same as voltage times capacitance. So in this case we'll have C1, and Q2 will have V times C2, and that of Q3 will have it as V times C3. So that is to say, we'll have the total charges being given as VC1 plus VC2 plus VC3, and since the voltages are the same, then we'll have total charges being given as voltage times C1 plus C2 and plus C3. And check it out, there is a combination of the capacitors, actually there is a combination of the capacitors that are in the circuit. And what is that combination? It follows the linear order. So in this case, the equivalent capacitance, that is the total capacitance, will be given as C1 plus C2 plus C3. So that's how we find the total capacitance, and for the capacitors that are connected in actually a parallel. So we just have to literally add, in a linear order. So keep that in mind. And let's say we have the following capacitors being connected in a parallel. Let's say we have, capacitor 1 that is given as 2 farad. Let's say capacitor 2 being given as, let's say, 5 farad. Let's say capacitor 4 should be capacitor 3 being of, let's say, 6 farad. So what is the total capacitance or equivalent capacitance for this? So now, since they are connected in parallel, we'll have it as 2F plus 5F plus, and that should be that of 6F. In this case, we'll have it as 13 farad. So as you can see, always that for the capacitors that are connected in parallel, their total capacitance is greater than the largest capacitor, and that for the capacitance. So keep that in mind. So which means the more we are adding capacitors the more we are adding the capacitors in a parallel, the more their total capacitance is actually increasing. So keep that in mind. Now let's say we have this question. Now we have, this is a typical, actually a circuit with capacitors. Now the question says find the equivalent capacitance in the circuit and also find the charges stored across each capacitor. So now how should you have it? As you can see, this is a typical, actually a series circuit, and with capacitors given as C1, C2 as well as the C3. This is C3, and this is the pressure difference being applied. So in order to have, what should be the equivalent capacitance? So now the equivalent capacitance, since these are in series, we'll have it as 1 over total capacitance is equal to 1 over should be 2 plus 1 over 10 and a plus 1 over 7. We'll have that. And let's combine this. That will be given as 1 over TC, that will be equal to, we'll have 10 plus 2 divided by 20 and a plus 1 over 7. So have 1 over TC, that will be given as 12 divided by, and that should be, so whichever the way you combine those fractions, it's okay. 1 over 7 in that case. So have 1 over TC, that is the total capacitance, that is the same as, we'll have 12 times 7. So what would be that? It's not 12 times 7, no, have it as 84. So have 84 plus 1 times 20, that is 20, divided by, and that of 7 times 20. So what is 7 times 20? We have it as 144. It should be 140. So have 140. Then that is that. Butterfly method is one of the best way in which you can have to add fractions or subtract. So we have 104 divided by 140. Then the cross multiplication will have it as 104 TC, that is the equivalent capacitance, is equal to 140. Then what is TC? We'll have it as 140 divided by, that is 104. So what would be that? So 140 divided by 104, that will be given as 1.35. So have it as total capacitance being given as 1.35, and that should be in farad. Now should be given in active farad. So now we have the total capacitance, the total capacitance. That is that. The next, we should have to calculate the charge stored across each capacitor. So now, since this is the series circuit, and notice the charge bar should be the voltage across each capacitor. By the way, it should be voltage across each capacitor. So should be the voltage across each capacitor. Should be the voltage across each capacitor. Now, since this is the series circuit, at each and every capacitor will have the same charges being stored. Then we should have to calculate the total charge in the circuit. So what is the total charge? The total charge will be given as the voltage times the capacitance, of which the capacitance is the total capacitance. So have it as, and the voltage from the battery will have 60 times what is the capacitance, we have 135, 1.35. We'll have it in a kilo ohm, by the way. In this case, we'll have 60 times 1.35. So that is 81. So have 81 kilo ohm charges that are being stored at each and every a capacitor in this circuit. So have here 81, and also here 81, and also here 81. Then now, since we have the charge and also the capacitance, we can be able to find the voltage across each capacitor there. And in that case, we'll have the voltage across capacitor 1. That will be given as the charge divided by capacitor 1. That is, what is the charge? 81 divided by what is the capacitor 1? We have it as, should be 10. So that is the same as 8.1. Of course, that is 8.1 should be volts. Then the voltage across capacitor 2, have it as the charge divided by, what is the capacitor 2? That is be given as, should be 2. That is to say 81 divided by 2. That is 40.5. So 40.5 volts. And likewise, also do the same with our capacitor 3. So that's how we should have to understand about in that way. And now let's say we have this also another question, and where we have this is the circuit, with the capacitors given as C1 2 farad, and C2 10, C3 1, and C4 5. And this is the pressure difference in that way. So we should have to calculate the equivalent capacitance in the circuit. Now, in this case, this is actually a parallel circuit because there is a presence of the junctions here. And another notation for the parallel circuit is that we have more than one loop. So this is the loop 1 and this is the loop 2. And that shows that that is really the parallel circuit. And apart from having the junctions, they can also be able to note the parallel circuit in terms of the loops. So if we say loop is the completely closed circuit, that is a loop. So in this case, this is the complete circuit, bounded by this branch. And also this is the complete circuit and bounded by the same branch, no matter what part that is. And now we know that this is a parallel circuit. And now we should have to understand about, sometimes you can have the capacitors being connected in, let's say, in a series, yet the circuit is in actually parallel circuit. Let's start with, let's say, a C1, actually C2. C2 is connected in this wire, and it is alone there. And the C3 is actually connected in this wire, it is alone there. So hence, this capacitor and this capacitor are in parallel. And let's go for along this wire. So along this wire we have, a capacitor 1, capacitor 4, and also the potential difference. All those are connected in a series circuit since they are connected in the same wire. So first thing, in order to find the equivalent capacitance, First thing, we should have to calculate the total capacitance for these two, since they are connected in a series only. So we just have to calculate them first, then we'll combine them with the other two. So what would be that? So we may say let total capacitor for C1 and C4 be, I'll call it as, let's say, N. Now since they're in series, you know the principle behind. We'll have 1 over N, which is equal to 1 over 2 and plus 1 over 5. We'll have that. Using the butterfly method of adding fractions, we'll have 1 over N, which is equal to, have 5 plus 2 and divide by 10. That is 1 over N is equal to 7 divided by N. That is now 7N is equal to 10. So in this case, N will be given as 10 over 7. So what is that one? So in that case, we'll have 10 divided by 7. That is been given as 1.43. So we have it as N is equal to 1.43 farad. That is for these that are in actually a series. So that is that. So now as you can see, the circuit now will be reduced. The now circuit will be reduced. We'll have it as this case. You know, that is this, actually that is the potential difference. Now the circuit will be reduced to this. That is, you know, Cn. We'll have that. Now the circuit has been reduced to this. Now we have it as this. So where this is, you know, 60 volts, and this is 1 farad, this is 10, and what is this? We have it as 1.43 in that way. Then we should have to finally calculate the equivalent resistance. It should be, so for that, should be equivalent capacitance. So now both are in parallel. We'll have to calculate the total capacitance and for those. So that will be given as 1.43 and the plus 1 and that of plus 10. And what is the total there? So 1.43 and plus 1 and plus 10. That is 12.43. So the total capacitance is given as 12.43 farad. So that is the total capacitance in the circuit. So whichever the way, if you have the complex actually a complex circuit, start reducing it by actually one by one by looking at either you can start reducing that one using, let's say, the capacitors that are in parallel, then you have until you have the final actually circuit. And the next is, since we have the total capacitance, that is equivalent capacitance, that is 12.43 farad, then we need to have the total charges in a circuit. So what is the total charges? So the total charges will be given using the formula, you know, the capacitance times the voltage. Where capacitance, this one is the total capacitance. That will be given as 12.43 and the times, that is the voltage from the battery will have 60 volts. And that will be, what is 60 times that one will have 745.8 coulomb charges. So those are the amount of charges that are in the circuit in that way. So by the way, this is the answer to the first question, that is equivalent capacitance. So we have that. Then we are to answer the next question, that is the amount of charges stored across each capacitor. So towards the second question, that's when now we have started in this way. So keep that. Now, in that case, you should have to understand that these actual total amount of charges are all the way from the potential difference, which is of 60 volts. Now, you should have to understand that the other two capacitors are connected in series with respect to the actually a battery. Now, since they are both in series, it means the flow of the total charges, that is actually 745.8 coulombs charges. It is the same for this as well as the same for this. So since they are both connected in the series with respect to the battery, so which means this total amount of charges are the same flowing here and also the same flowing here. And also that corresponds to have the different potential difference across here and also across here, since they are connected in the series circuit. Actually, since they are connected in the series. So if that's the case, then we are going to have the potential difference across actually capacitor 1 and also across capacitor 4, since they are in series with the battery. So we cannot say the potential difference here is the same as 60 volts because they're in series with the battery. So they'll have different actually the potential difference. Now, what is the potential difference across capacitor 1? In that case, we'll have charge divided by the capacitor 1. And what is the charge? That is the total charge. 745.8 divided by what is the capacitor? Should be 1. We have it as 2. So now in this case, we'll have 745.8 divided by 2. That is 372.9 volts. That should be that. Okay, anyway, let's have that. And what is the potential difference across? It should be the potential difference across, and that should be capacitor 4. So have V4 being given us, that is the charge, which is the total charge, 745.8 divided by what is the charge for that is given as 5. So what will be given us that? Now have 745 point, and that should be 8. Now divide by, that is 5. We'll have it as 4 should be 1, 49.16 volts. That is the voltage across capacitor 4. Of course, it is not making sense because the voltage from the battery is 60 volts and compared to the voltage across here and also to the voltage across here. But the emphasis is that you should have to understand that upon having the voltage across here and the voltage across here, we'll add the two voltages. Then upon adding, we'll subtract from here. Then the remaining voltage will be the one flowing in these two capacitors because they are in parallel towards one another. So upon having that one, we'll be able to find the amount of charges stored here and also amount of charges stored here. That is the point of interest. So we are calculating the voltage across here and also across here because we know that these capacitors are connected in series with the battery. So we know the principle behind the series circuit, that the voltage is shared. So in this case, the voltage has to be shared here and also has to be shared here as well. But the remaining voltage is going in the parallel circuit for these two guys. So we'll have that. So that's how you have to understand about the calculations behind those of the combination of the capacitors in parallel circuit as well as the series circuit. Of course, there is a set of examples and practice questions that you can go for. So try to go through those questions, and you should have to mastermind on how we can be able to find the equivalent capacitance in a series circuit as well as the parallel circuit. That is the beginning of everything. Then from there, you should have to understand about the actual properties of these actual circuits. That is the series circuit as well as the parallel circuit, in the sense that in the series circuit, the voltage is shared, but the amount of charges stored is the same. While in the parallel circuit, the voltage remains the same, and the amount of charges stored are the ones that are being shared. And the voltage is the same, provided there is no capacitor being connected across in series with the battery. Otherwise, you need to have to calculate the voltage across that particular actual capacitor. Then you have to subtract from the total voltage from the battery. Then the remaining will be the one for the capacitors that are in parallel. That is, if we have a circuit in which the capacitor is connected in series with the battery, but the other ones are in parallel. So keep that in mind. Thank you.